This is second part of chapter 4. In part 1, we talk about Newton's first law and second law. Newton's first law is if an object at rest continue to stay at rest, or if an object moves in a constant velocity, it maintains that velocity unless there is a net force acting on it. And Newton's second law is acceleration, force, and mass relationship. Acceleration is equal to force, net force divided by mass, and then we can rearrange and we can write net force of an object is equal to mass times acceleration of the object. This equation has a particular direction because acceleration has a direction and therefore force has a particular direction. Now we move on to Newton's third law of motion. Third law states that when one body exerts a force on a second body, the second body also exerts an oppositely directed force of equal magnitude on the first body. So let me explain this statement a little bit. Uh, let's consider this cartoon. Let's say I am pushing this wall with a force. Let's say this is a wall and I am pushing this wall with a force. If, let's say, 50 Newton force. So this is force by me on the wall. Now, according to Newton's third law, this wall pushes me with the same force opposite in direction. This force is negative if this is a vector. I'm not sure. This is a vector, so this is called force by wall on me. So these two forces are very similar. The first one is force by me on the wall, and the second force is force by wall on me. By me on wall, or by wall on me. So I can write this force by me on the wall, which is equal to force by wall on me. Notice the subscripts switch when, so first one is by me on the wall, second one is by wall on me. So if you consider the direction, one is negative value of the other force because those two forces are opposite to each other but equal size in magnitude. That is basically Newton's third law says. If you exert a force on an object, the object also exert a force on you, which is equal to the force you exert on the wall. So in this example, astronaut is applying a force onto this spacecraft, and that force is to your right, and this force P is a positive value. And because according to Newton's third law, the spacecraft also applying a force on the astronaut, which is on the opposite direction, therefore negative P. So now if you know the mass of the spacecraft, which is given 11,000 kilograms, and if you know the mass of the astronaut, which is 92 kilograms, you can calculate the acceleration, because from Newton's second law we learned that net force is equal to mass times acceleration. If you want to calculate the acceleration, we can use net force divided by mass. So if you want to calculate the acceleration of the spacecraft, you have to use the net force on the spacecraft, which is plus 36 Newton, divided by mass of the spacecraft, which is 11,000 kilograms. 11,000 kilograms. And instead of writing newtons here, I'm going to write kilograms, because newtons is kilograms, meters per second square. So the reason I wrote like this is, here you have kilograms, here you also have kilograms, you can cancel. So when you calculate this, solve this problem, acceleration of the spacecraft, you will get the units of meters per second square. So in this, here you will see acceleration of the spacecraft is equal to force over mass. This is net force, which is plus 36, because you apply a force in this direction. Astronaut apply a force on the spacecraft, which is plus 36 Newton, and this is mass of the spacecraft, which is 11,000, and you have a very small acceleration, because a spacecraft is a lot heavier than astronaut mass. Therefore, this is a very small acceleration. But on the other hand, if you calculate the acceleration of the astronaut, which is negative P, because negative is the force on the astronaut from the spacecraft, and which is equal size in magnitude but opposite in direction, and divide by his mass, and you will get negative 39.39. So you can compare these two accelerations magnitude wise. You will see astronaut push, when you apply a force, astronaut will push us to this direction because of the force by spacecraft on the astronaut. 30.39 meters per second square, 0.39 meters per second square. Now we move on to a different topic, types of forces. In this section, we going to learn several different types of forces, and all these forces we going to talk fall onto two main categories: fundamental forces and non-fundamental forces. The fundamental forces are the forces this universe made out of, the gravitational force and strong nuclear forces, the force between atoms, and electroweak force. So these three forces are fundamental forces. And next page we going to talk about non-fundamental forces. Friction, it's like a friction on a car tire, or friction on two moving objects on touching each other, and tension in a rope, normal or support force. We're going to take examples from each of these forces, and we can see how we can calculate the magnitude of the normal force, magnitude of the friction, and tension. So in next few slides we will take one force at a time and discuss how we're going to calculate each of these forces. Let's consider two masses, M1 and M2. Mass of particle 1 is M1, this is particle 1, M1, and particle 2 is M2, and the distance between the two particles is R. And according to Newton's law, we know that if you have two particles or objects, one particle exerts a force on the other particle by particle 1 on particle 2, and also there's another opposite force by particle 2 on by particle 1. These two forces are equal size in magnitude but opposite direction. So from Newton's law of universal gravitation, we can calculate the magnitude of this force. So magnitude of this force is given by this equation. Force F is equal to some gravitational constant times, this is the constant, G, gravitational constant 6.673 times 10 to negative 11 Newton meter square over kilogram square. And also this force is proportional to mass of the particle 1, and also this force is proportional to mass of the particle 2, and this force is inversely proportional to square of the distance between the two particles. So force between two objects or particles is given by gravitational constant, which is a given constant, mass of particle 1, mass of particle 2, divided by distance square between them. Let's consider a very um, let's consider a example. Let's say particle 1. Uh, uh, this is particle 1. Mass of particle 1 is 5 kilograms, and I'll consider another particle. Mass of particle 2 is 2 kilograms, and the distance between them R is, let's say, 3 meters. So force, according to the Newton's law of universal gravitation, gravitational constant G times mass of particle 1 m1 mass of particle 2 divided by r square. So this is equal to G times m equals 5 kilograms times 2 kilograms divided by r is distance square. 3 meter square, and you can substitute G from 6.67 times 10 to negative 11. You can look up the number, and then you can simplify this force. So this is particle 1 on particle 2, which is same as magnitude particle 2 on particle 1. If you want to get the direction, you can put a negative sign because it's in opposite direction. Here's another example given in your textbook. So G is 6.67 times 10 to negative 11 Newton meter square divided by kilogram square. Mass, we know unit of mass is kilograms. M1 is 12 kilograms and M2 is 25 kilograms, and the distance R is 1.2 meters square. So meters square you can cancel with meters square, and also mass kilogram square, kilogram you can cancel, and you left with unit Newton. We know when you calculate the force, your final answer supposed to have the units of force. So when you substitute right units, you end up with the right unit for your final answer. So at the beginning of the chapter, we talk about mass. Mass, we said it's stuff in an object. So, and also we talk about scalars and vectors. We know scalars are quantities which has a magnitude, and vectors has a magnitude and also direction. So mass is a scalar because it's just a quantity but no direction. How about weight? Weight is somewhat similar to mass, but it has a direction. So weight of an object near Earth's surface is its gravitational force that exerts on the object. Gravitational force that exerts on the object. So the weight always acts toward the center of the Earth. If you have a object, let's draw a small sketch. If you have an object near Earth, let's say this is the Earth's surface. We know according to Newton's third law, if you have an object, there is a force by object on Earth. And similarly, by Earth, there's a force on this object, by Earth on the object. So this force, we call it weight. So we know how to calculate the force, gravitational force, G, mass of the object. Let's say mass of the object M, if you know the mass of the object, and also mass of the Earth, and the distance between the object, and the Earth. Basically, it's equal to the radius of the Earth, because close to the Earth's surface means we can consider this object is on the Earth's surface, because the distance from Earth to like couple of 100 meters or couple of 1,000 meters or even higher value is very small compared to the radius of the Earth. Therefore, we consider the distance between the center of the Earth to the object is approximately equal to the radius of the Earth. If you know the mass of the Earth, mass of the object, and the radius, we can calculate this gravitational force. So weight is equal to G, mass of Earth, M, mass of object, divided by R square. And this thing is like G. Therefore, we can write W, weight, equals mass times gravity. So definition of a normal force. Uh, uh, at this time, by this time, we talk about a couple of different types of forces. Force is a common name, but in next few slides, you will see there are different types of forces, and we just talk about weight, which is a force. Weight, we use W for weight as a notation. Weight is a force on an object due to the gravitational field. Is a gravity force on an object, which is equal to mass times gravity. And now we're going to talk about another force, normal force. Normal force. We use F and with a small letter M. N means normal force. And next slide, I think we're going to talk about friction. it's another type of force. We use lowercase f for friction, and it's another force, we call it tension. We use F, T for tension, lowercase f for friction, normal force F in, weight W mg. So all these are forces. Forces, its force is a common name. Under forces there are a couple of different types of forces, and I expect you to memorize these different notations when you work on problems. T for uppercase T for tension, lowercase f for friction, normal force we're just going to talk about is Fn, and weight W, gravitational force mg. Okay, what is normal force? In Newton's second law, third law, we talk about if you apply a force onto another object, the other object also apply a similar force but opposite direction, which is equal to the magnitude of the force you apply on that particular object. Uh, so if let's take this brick. We know it has a mass. It has a mass. So because of the mass, and we know there's a gravitational force on this brick from the earth. The magnitude is g, and that is always towards the direction of the earth. So this W, weight force, is mg. You cannot have just one force. You have to have a similar force but opposite direction in order to balance that one. So if this brick is sitting on a flat surface, this normal force, we define a new force. It's called normal force, which is perpendicular to the surface or normal to the surface. So that force is Fn. So in other words, normal force is same as weight magnitude wise. So therefore I can write magnitude of the normal force is equal to mg. If the normal force is greater than W, then you have a net force along y direction. If the weight is greater than normal force, then there's a net force along and negative y direction. This is unstable case because you cannot have just a net force, because we know that according to Newton's second law, force equals mass times acceleration. If you have a net force, you will have acceleration, or you will see this brick start moving. So if the brick is not moving, means there is no net force. If there is no net force, these forces, weight force and the normal force, needs to balance. So therefore Fn is equal to weight force, which is mg. Let me give you an example. Let's consider a mass m, let's say 10 kilogram. M is 10 kilogram, and I can ask what is the normal force. So we know the normal force is perpendicular to the surface, and I can write Fn. And if I ask what is the magnitude of the normal force, we know that it has a mass, therefore it has a weight. Weight is pointing down, W, which is equal to mass, 10 kilograms, times acceleration due to gravity, 9.8 meters per second square. So approximately, this is approximately 10, so 100 kilograms meters per second square, or you can write 100 Newton. So normal force, we know that equal to W, weight, because this mass is not moving, and therefore normal force is equal to W, which is equal to 100 Newton. Let's consider another example. Let's consider a mass in 6 kilogram mass sitting on a flat surface. And if I ask you to draw the forces acting on this mass M, you can now know that there are two forces. One is the weight force because of the gravity, and there is a normal force because this mass M is on a surface, and from this surface there's another force on this mass on opposite direction. So this is the normal force Fn, and also it has a weight force. So these two forces are equal in magnitude but opposite in direction. So W equals mass, which is 6 kilograms times, instead of 9.8 I will write 10 because it's easy for me to multiply, and your meters per second square. That's the acceleration due to gravity G, which is equal to 60 Newton. Okay, so therefore I can write if normal is equal to 60 Newton. I'm going to change this a little bit. Let me give you another example. Let's assume you have two bricks. So first one, you had one block, 6 kilograms, and now I'm going to add another mass on top of that one. Let's say this one is, mass of this one is 7 kilograms. Okay, so now you have a weight because you have two masses. So mass 6, the total mass is 6 plus 7, so which is 13. So if you calculate the weight force, which is equal to, you see the length of this arrow is greater than this because now your weight W is total mass 6 plus 7. This is mass times gravity 10, which is 130 Newton. So if you calculate the normal force, because there are normal force which is equal to 130 Newton. So because of this additional mass, there's a force on this brick. That force transfer onto this surface. Therefore, you have a more normal force, because every time when you add something, your normal force will go up. So this is an example on your textbook. I think the mass is like 1.5 kilograms. Because of this mass, we know a weight force W, which is equal to 1.5 times 10. This is mass, this is gravity. You get 15 Newton. So in addition, you push this brick towards downward direction with another force. So you have two forces, 11, and there's another force, 15, because of weight. Both those forces are this direction. So 15 plus there's another force you apply from your hand. So you get 26. So now your normal force is, you have to balance this force pointing down. Therefore, your normal force is same as that force, but opposite direction. So therefore, your normal force become, if N become 26. So this is 26 Newton. And in this case, same mass, 1.5 Newton. 1.5 kilograms, and if you multiply by 10, you get 15 Newton. This is weight force. Instead of pushing down, now you lift with the force 11 Newton. So you have now two forces. One is 11 point going up, and you have another force. One is 11, one is 15. This is weight. This is the force you apply by hand with the rope, and you have a net force along this direction, which is equal to 4 Newton. That is your net force. So your normal force going to be same as that net force, because that's the net force you have due to those two forces, and that net force is Fn, which is equal to 4 Newton. Okay, so normal force, if you notice, is always equal to the net force from the additional forces you apply. Okay, let me give you one last example before I go to the next step, next topic, because I want to make sure you understand the meaning of the normal force. So let's say this mass is 20 kilograms. When you see a mass, you know because of the gravity you have a weight. No matter what, you can write that W, weight force, is mass 20 times 10, 200 Newton. In addition to that, let me give you a couple of different. You apply another force pointing down on this block. Let's say force 1, which is 5 Newton. Okay, and let's say I have another force. Let's say F2, which is 8 Newton, and I have another force F3, which is 5 Newton. And let me draw one last force. On this object, F4, which is 7 Newton. So my question is, what is the normal force? So before you calculate the normal force, first thing you need to calculate is what is the net force. Net force on this block. You can write all the forces pointing down. You have a weight force 200 Newton, and then you have another force F1, which is 5 Newton, plus you have another force 5 Newton, 210 pointing down, and write down the forces going up. You have a 8 Newton force, plus you have a 210 minus 15 Newton, 195 Newton force pointing down. So your normal force, basically you have a surface, you have one force 195. This force needs to balance with the normal force Fn. which is equal to 195. This is the answer. Apparent weight. Um, when you in a vertically moving objects, when you are inside a vertically moving objects like for example elevator, depending on the direction of the elevator travels, if it is going up or downward, your real weight, your weight can be changed. Then because of that change, we call, if you are inside a elevator, we know you can use Newton laws to calculate the force or acceleration. So if it, let's say, if since you it's vertical, you can write Newton's laws in vertical direction, mass times acceleration along y direction. So Fy is the net force. So if you are inside the elevator, you have your weight, and also you have your normal force, Fn. Weight equals normal force pointed that way, and then mg is your weight, W. Therefore you put a negative sign because when you apply Newton's laws, you have to apply for a certain. So therefore make sure you use the right signs, because weight is point down, so you put a negative sign. So net force is normal force minus weight, which is equal to mass times acceleration of the elevator along y direction. So the normal force is your apparent weight. This is the, if you have a scale inside, this is the force you see on the scale, which is equal to your actual weight plus mass times acceleration, because of the elevator is moving. If the elevator is not moving, your mass times acceleration of the elevator becomes 0. Your normal force is same as your actual force, weight. But if the elevator is moving, you, depending on the direction, you have a plus sign or minus sign. If the elevator going down, you get a minus sign. If the elevator going up, you get a plus sign, which means your normal force, apparent weight, is higher when you on an elevator moving upward. When you have two objects touching each other, and when you want to move one surface, when you apply a force onto one surface, and the second surface or second object apply a force opposite to that direction, so it always try to oppose the motion of the first object. So this force is coming from the area those two surfaces touch. Depending on the nature of the surface, two surfaces, it is easy to slide or it is hard to slide. So the force the second object apply on the first object, we call it frictional force. So friction has two parts: static and so the static friction is we by experience we know if you want to move a like a couch or very heavy object by applying a force. Initially, if you apply a small force, you cannot move it. If you increase that force, you maybe slightly able to move it, or if you keep increasing the force, at one point you see that object is moving. So the initial force you apply balance with a force on the two surface, and if you increase the force, the additional force you apply is balanced with the force acting on the surface from these two surfaces. So that type of friction, we call it static friction. Static friction. At one point, this object moves, and then when the object start moving, that the friction between the two surfaces, we call it kinematic friction, and we use Fk. Kinematic friction. So this table shows a two-column static friction and kinematic friction. Notice static friction, the force need to require at the beginning is large because you have a static friction. So the force, uh, static force is static frictional coefficient mu k times normal force. But when the object start move, it is easy to move that object because the applied force becomes smaller because your kinematic friction is small. So therefore your frictional force is mu k. Now it's moving, therefore coefficient is smaller, and Fn. Normal force not going to change because it's equal to mass, weight of the object. The final force we're going to talk about in this chapter is tension force. Tension force coming from cables and ropes which transmit a force. We call it tension. We use uppercase T for tension. Let's see how we're going to calculate the magnitude and direction of the tension. So in this first figure, you have a block and connected with the rope, and you apply a force, tension force, and we know if these two surfaces, this is uppercase T, and if these two surfaces touching each other, we know there's a friction, lowercase f, which is equal to, if it is not moving, static friction times normal force. You can calculate normal force if you know the mass, which is equal to weight. And if you know the static frictional coefficient, if this thing is not moving, you can calculate F, and which is equal to T, because F is opposite direction, T is towards to your right, so T is balanced with friction, therefore friction force is same as T. So here we use a massless rope. We know every object has a weight, but compared to the mass or this block, we can assume this is massless. The reason we call or assume a massless rope, because if you consider a mass of the rope, then we have to consider the weight force of the rope. Then it may become complicate our calculations. Therefore, it's reasonable for us to assume the mass of the rope is negligibly small compared to the mass of this person and mass of this block. So this rope will transmit tension from one end to the other end. So this person holding this rope and this tension transmit to the other end. So you have tension and you have a mass. We know this mass has a weight force, W. If it is, the whole thing is not moving up or down, you can say W is equal to T. W is equal to mass times gravity. And if you know the mass, if you know the mass, if you know the gravity, which is 9.8, you can calculate W, then you can calculate tension. So definition of equilibrium. Let me go back to the previous problem. So from the card, you can draw the forces T and mg, which is equal to weight. And if you use the Newton's law, net force is equal to mass times acceleration. If this is not moving, its acceleration is zero. So the normal force is W minus mg. I'm sorry, this is net force. Newton law says net force. So net force is, one force is mg, the other force is T. T minus mg equals mass times acceleration. If the acceleration is equal T minus mg, T equals mg. So you can calculate tension, which is equal to mg if it is not moving. So in this case, we can say the force along y direction, net force, is equal to 0 because acceleration is 0 because it's not moving. Net force is equal to Fy net is equal to mass times acceleration. If the acceleration is 0, Fy is equal to 0. This is that. This is end of this chapter, and I will post couple of examples how to calculate net force, weight, and friction in in a in a different presentation, and I will do couple of problems from your textbook, and I will post.